Welcome to today's lecture on raster images as a part of the computer graphics course at KAUST. Today we will be talking about the standard representation of computer graphics or the standard input for various computer graphics applications, namely a raster representation. Raster image is basically an image which is displayed on various devices in a form of an array of pixels. And this is what we will be covering today with various aspects to it. This is the most standard representation nowadays, and therefore, before we dive into 3D computer graphics, we need to understand how the picture eventually gets displayed on the final display. The discretized representation can start already at the input devices. We know that digital cameras are raster devices or scanners as well, and they perform sampling of their visible environment. And with a sensor, which is an array of sensing elements, they store or capture this information in form of discrete samples. Similarly, even if we describe through computer graphics a continuous space, at the end of the day, the representation gets rasterized because it will be represented finally at a certain display. This display can be an LED screen, it could be a projector, but it could be also a printer. So image is a grid of pixels, and it is a two-dimensional grid of pixels. Pixel is an abbreviation for picture element. But this is not the only discretized representation we are using in computer graphics. We also use a so-called volumetric representation, which is a grid of voxels. So this is a three-dimensional array of volume elements. The resolution of image or volume is typically defined through the amount of samples. Please keep in mind that discrete representation is not the only representation, and this holds also for the images. We will not be covering a vector representation in today's lecture, but it is important to keep in mind that even an image which looks rather realistic, and one would be tempted to interpret it as an discrete representation, can be defined through vector representation, such as the diffusion curves technique as described in some recent research work at SIGGRAPH 2008. Even though this representation would be a vectorized representation internally, if we will be displaying on a display, at some point in time, this representation would need to be rasterized. What are the basic hardware which are used for representing raster images? There are various types of displays. Nowadays, we are mostly using the LED emissive LED displays. And the principle is that they have a set of an array of small diodes which could be turned on or off at various intensities, and the combination of the turned off or on diodes forms an image. We are also perhaps familiar with the so-called LCD screens. Those are liquid crystal displays, and they are not emissive, they are transmissive, meaning that they are transmitting light, but they are not light source themselves. They need a so-called backlight, as shown in the figure, which shines on the LCD hardware, and it will be selectively enabled to pass through the LCD hardware, which consists of two polarizer filters and through a so-called liquid crystal, which can, based on applied voltage, can change its geometry and can help a light to change polarization. This can be shown on the images on the left. On the bottom, please see first where you can see that this is when the liquid crystals are turned off. So we will have a backlight light, and then which is unpolarized, and then we will have a horizontal polarization filter. So only the polarized light, which is oriented horizontally, will be passing through this filter. And then we have the liquid crystals, which are then in an unmodified state without applying any voltage. And after them, there is another layer of a vertical polarization filter. But we know that already the light has been polarized horizontally, so the vertical polarizer will mean that there will be no light passing through outside. This is a correct behavior for the turned off liquid crystal element. If we apply voltage to the liquid crystal, this alignment of layers will change its shape. It will twist, and this twist will enable the light also to change polarization from horizontal to vertical. So in a full voltage, the light will be completely turned vertically, and with a partial voltage application, there will be just a partial change of polarization orientation or direction. But even such a small change will be then visible only partially, but still on the liquid crystal element. So based on the combination of various voltages for all these pixels, millions in fact, sorry, thousands in fact, they will be millions in fact. There will be they will form an image. Now we have typically a color displays, and these color displays are realized through the diodes or liquid crystals, which are of different colors. We are using the three primary colors of red, green, and blue, RGB, which at shining at different intensities are forming us a different color. So if all three of these so-called subpixels within one pixel will be shining at a full intensity, they will form a white light. If they all will be turned off, they will be forming a black representation, black pixel representation. We will be talking about this in a moment on some slides later. Let's stop shortly at not output devices, but input devices, which we can first, as a typical input device, consider a camera, which is nowadays present in everybody's pocket in the cell phone. And these cameras would typically have an raster where they are having just sensitivity to particular wavelengths for particular sensor element, either red, green, or blue. And this mosaic, as you can see it on the right-hand side, will be then in a post-processing step converted into three layers of or three channels which are continuous. So there will be a green, red, and blue channel represented for each pixel, even if the sensor was providing one channel per sensor element. This process is called demosaicing, and one needs to keep in mind that even if the resolution of such a sensor would be very high, its real resolution in terms of color, RGB triplet, will be lower. What we can also see here is that the green color is represented the most, and then the red color is the second most frequent color, and the blue color will be the least frequent one. And this has something to do with our own resolution in these three color channels, where we can sense the green or mid wavelengths in the perceive them strongest, while the blue we are perceiving the least. In a digital camera, such a sensor will be typically also combined with optical elements, which are then changing the rays so that the rays are then passing on to the sensor element, as we can see on the image on the left. The next device which we are also frequently using are scanners, which is also an input device. And scanners have typically not a 2D sensing array, but only 1D, or maybe 1D for each channel. So we can have a three channel arrays, and those will be then scanning the input, typically a piece of paper which is put into the scanner by seeing one scan line at a time and sensing that scan line at a time, but by continuous movement along the flatbed scanner area, we can scan the entire document. Now we have a broad overview in which we see that how the input or output devices are represented through a hardware. Let's abstract from the hardware, and let's define what is an image, what this array of pixels. So an image is typically a set of samples which are for 2D images indexed in 2 dimensions, and they would typically go from some XY coordinate representation, which is the input, which is an input in of a rectangular area that is a subset of the R2 plane. The output of the image function will be the value, the intensity of a particular sample and pixel, which would typically be in the output in real values, positive real values, and if we have a color image with 3 channels, it will be R plus 3. We are typically indexing the elements of an image by I would be the column and J would be the row, and we are starting from bottom left to top right. So pixel with index 0, 0 will be at the bottom left, while a pixel with nx minus 1 and y minus 1 indices will be on the top right. Nx and ny are the resolutions of this, is the resolution of the image. Keep in mind that this is just a definition which some particular system implementation might have a different representation. So for example, in OpenGL, which you will be dealing with at some other courses in computer graphics, you will have the top left element will be the 0, 0, and bottom right element will be the nx minus 1 and y minus 1 indices. Here we can see the image with the samples, with the pixel elements, and with a certain area of that pixel elements to which it is associated with. And here we can see that an pixel element 0, 0, pixel 0, 0 is actually defined in an area minus 0.5, minus 0.5, this point, to 0.5, 0.5. This is important to keep in mind. Therefore, also the upper end of the rectangle, it will be defined as nx minus 0.5 and y minus 0.5, so that the pixel element is the starting pixel is actually placed at the position 0, 0. If we are talking about resolution, we are often referring to certain resolution or some hardware capabilities in terms of megapixels. Normally and often in computer science, we are defining our sizes by powers of 2. So 1 megabyte would be an 2 powered by 10 bytes. This is, however, not the case in terms of megapixels. Here, 1 megapixel means 1 million pixels. So just that it is a small difference of elements, but still one should be aware of this slight difference. The pixel bit depth, so how much memory are we associating with a particular pixel value, can be varying. If we are generous, so to say, we can use 32-bit floating point values, and it could be in principle defined in positive real as a positive real value, but often we are clamping the values within a channel into the range between 0 and 1. So for standard devices and for standard 3D graphics, we will be using, like, for example, texture images, and so we will be using 8-bit representation for each channel, meaning that we just need 1 byte to represent one channel of a texture. If our texture has RGB values, then we will be using 24 bits, 3 bytes. And each channel will then be defined between 0 and 255 different values, where 0 will map to 0 and 255 will map to 1. These are low dynamic range displays, standard displays, but we can also use the concept of high dynamic range displays or imaging, which uses much higher resolution. So for example, high dynamic range imaging cameras would be using 32-bit floating point representation for each channel. So, which means 32-bit times 3. This will be a much higher bit depth, but it will also result in much bigger memory consumption. So here we have common formats which are used in graphics or imaging applications. We are the shallowest bit depth would be 1 bitmap, which where the pixel is either defined black or white. This is perhaps a reasonable representation for some textual displays. These displays will have to have a very high resolution so that we do not see too much of edgy representation of the text, for example. So there will be very high image resolution, but the bit depth will be rather shallow. Standard representation for RGB fixed range will be 8 bits per channel, and this is referred to as low dynamic range graphics. Displays are typically having 10 bits RGB fixed range. So they are in fact capable of displaying bigger range than an LDR graphics. So typically each channel will have a possible display various shades to be displayed around 1000, not only 250. For input imaging, we are using even more resolution, bit depth, sorry, which might be even 12 to 16. And then, if we want to create a final picture, like a JPEG, this range will be then converted into a low dynamic range graphics. But this will allow us, for example, to choose the parts of the intensity distribution, which is the most interesting for us, and that one will be converted into the 8-bit fixed range, and the other values will be simply clamped to either 0 or 1 because they are not so important for that particular picture. In medical imaging, we are often using 16-bit grayscale representation. So, for example, computed tomography will be capable of delivering 16-bit representation, which is essentially capturing the transmission proportion of some X-ray beam. So this has a much higher resolution or bit depth, which allows the medical personnel to inspect the tissue properties in various contrast settings. If we are computing various colors for 1 pixel in the GPU hardware, for example, we are typically dealing with 32-bit representation. So the internal representation before the pixel is being computed, it will be 32-bit floating point times 3 for each channel. Very high resolution so that the intermediate computations are not suffering from certain artifacts. Only once we are computing the final color, then it can be then clamped to a smaller bit depth range. What are the typical resolution artifacts? Well, these are bit depth artifacts. Clipping is one artifact where, for example, we imagine our scene is having a very high dynamic range in itself, very dark regions and very bright regions, and then we simply clip the bit depth, and some areas which would still have very many different intensities of brightness will all be mapped to 1. So they will be all flat one color. Other artifact of bit depth might be quantization artifacts. So quantization means that we will see bands of colors. So if we will have less than 256 shades per channel, but only just, let's say, 16 or 32, we will experience this bending because many colors, which will be rather continuous tones of a color, will be then mapped to the same value. And that will create a kind of a bend in otherwise continuous gradients of colors. When we are dealing with displays, we often are referring to some calibration or correction of the display. And this correction, you might have often heard of gamma correction. So gamma correction is basically defining a middle value, middle gray value, so that the input value of 0.5 will correspond to a mid-gray value between black and white for that device. Often it might be that the input value without gamma correction will be 0.5 gray image, but in reality what will be displayed on that hardware will be something corresponding to 0.25 gray value, so much darker than the midpoint. And in this particular case, the gamma value will be 2, meaning that it's the gamma is the function power of 2 to map the input value into the final intensity. How can we calibrate a display in order to obtain a 50% shade of gray? This can be done by the following test or the following setup. Imagine that we are creating an array of pixels which will be alternating between black and white in both horizontal and vertical direction. So we will have somehow a checkerboard pattern. As this is a high resolution display, we will not be able to spot these individual pixels, but we will at typical viewing distance, but we will see it as a continuous shade of gray. And as there is 50% of black and 50% of white, the final percept will be the 50% of gray. So this is the value which we will be looking for. And we will, in our calibration setup, have on the left-hand side this checkerboard pattern, and on the right-hand side, we will be able to vary the gray level of pixels. And once we are able to define it so that both sides have the same level of gray, meaning that the border between these two parts is no longer possible to spot, then we have set up the input intensity to a value which will result into the 50% intensity between black and white. We can find such an intensity simply by calculating the, the gamma. So here, this should have been gone here, so you don't see some parts, but we essentially can calculate the 0.5 I will just use here instead of Imax, it should be equal to I times A, which is the input value, powered by gamma. Now, in order to compute what is the gamma value, we do not need the i's anymore, and the uh, the gamma will be equal to, so gamma will be equal to ln 0.5 divided by ln A. So this will be our gamma value. So in case, let's say that our setup will be the A will be, let's say, 0.71, then this will be the A. If this is 0.71 and the outcome is 0.5, this will mean that the gamma value will be equal to 2. This means that we will, instead of using an input value, we will correct it with the term which is A powered by 1 divided by gamma, so that in our display definition, we will have this corrected term. So instead of this term, which is shown here, we will have the ID on the intensity of a display is equal to I max times A 1 divided by gamma powered by gamma. And this will mean that we will have, and by this gamma correction, we will have a correct 50% gray value in the middle. We will, however, not have the perfect value at a quarter or perfect level of 3/4 intensity, because we didn't calibrate for that. But just calibrating in the middle gives us a fairly good calibration result for nowadays images, so that the intensities in between are reasonably calibrated as well. So, as I was talking about the quantization before, if we have high resolution floating point representation, and this is then rounded into the fixed range lower resolution, we can end up with quantization artifacts. And we can see here that the quantization goes into only 256 different intensity values, which is really the maximal intensity divided of the almost of the darkness powered by the gamma, and the same holds then for all other intensity values which are possible to achieve with that display hardware. We will be talking about color at a separate lecture, but first let me introduce some basic concepts of color spaces, such as the uh, primary colors. The primary, the primary colors, red, green, and blue, are in um, our concept of RGB color space together when they are all on at the maximum intensity are forming us the white color. And if, for example, only the green and red channels are on and the blue channel is off, we will have as an outcome a yellow color. However, this is a different concept than what we are typically used to. If we will be using a pigment, watercolors, for example, and we will mix the blue and yellow color, we will end up in green. So how come that the um, that the that this is that this system works differently? The answer is that while with pigment we are having at the beginning a white paper, and then the pigment is basically subtracting the white color to different forms of colors or different variants of colors. Here we are adding light. So we are having two different color space concept. One is an subtractive color model and another one is additive. So if we have the the colors are light sources themselves, so they are not subtracting light, but they are adding, then we are using the RGB color space in a way as described here. So you can try it out if you will use three different projectors, and one projector will be just projecting a red color, one projector will be projecting green color, and one blue, and they will be partially overlapping. You can in fact achieve such an effect as shown here. So, but we can also, through the subtractive model, we can create these colors as well, but in a different form of mixing. These two color spaces or color models, the additive color model and subtractive color model, are complementary to each other. So in the RGB space, we can form, if we will put each color channel on a separate axis, then we can span a 3D color space. And this 3D color space will be defined by three coordinates, like in 3D space in a Cartesian 3D representation. And if we will have this color space will be defined between 0, 0, 0 and 1, 1, 1. Now, at the 0, 0, 0, we will have the black color. This is the part which we do not see on our image. So the K is typically associated as a black. Because the B for black is already taken by blue. So, and if we will have the coordinates 1, 0, 0, then we will be essentially at this corner point where we are having the maximal intensity of the red channel. If we will have 0, 1, 0, we will be at this point of our color space, and at the 0, 0, 1, we will be at this position within our box forming color space. So what will be the so-called cyan color? This is a combination of blue and green. The cyan will be this point in our color space, which is the maximal value of the cyan, the most saturated representation. The yellow will be placed here, which will be the combination of red and green. And the magenta will be a combination of blue and red, which is this point in our color space. The white will be the value 111, which is positioned at this position. A question: what will be the color which will be indexed with 0.3, 0.3, 0.3? Such a color will be positioned on the, if we can say that here is the K, the 000, then it is, so this is at the back, which we cannot see, then this 0.3, 0.3, 0.3 will be placed on the diagonal somewhere here. And the diagonal between black and white is actually a grayscale line from black to white. So the 0.3, 0.3 will be a darker representation of some shade of gray. Let me spend a few minutes on compositing. So typically we are in our color representations dealing with 3 channels, which will be the, or 4 if for printing purposes, where we will be using the CMYK instead of RGB. By the way, the CMYK representation is used because the CMY would be typically sufficient, but with the pigments which are available, the black will be hard to achieve. It will be always somehow toned to various of these primary colors CMY. Therefore, the cartridges or laser toners of printers will be using a separate black, which is the CMYK channel. That's why it is a 4-dimensional space, which is somehow spent by the CMYK. So back to alpha compositing. If we have an image, it is usually indexed by either 3 or in this case CMYK by 4 different values, but sometimes we are adding additional value which will be the alpha, the transparency value, where the alpha value, if the alpha is equal to 0, will be completely transparent. Alpha equals to 1 will be opaque. And we can use the concept of alpha also in creating so-called transparent images. So instead of only having images which will be the RGBs values, we can have RGB alphas images, so that the transparency will be part of the image representation. Now imagine that we have 2 images, foreground image and a background image, as shown in this figure on the right hand side. And we would like to combine these 2 images together. So the question is how to define which pixel should be coming from the foreground image and which should be coming from the background image. Well, you can define a so-called alpha channel or a separate alpha mask, which will define that. And let's say for everything which is the alpha channel will be defining the transparency of the foreground. Well, with white, it will mean the alpha will be equal to 1. So in that area, we will be using only the foreground color, and we will see 0 of the background. And if we have the black outside of this around this triangle in the alpha channel, this means that the transparency of the foreground will be maximal. So it will be completely transparent and nothing from the foreground will be actually visible. And this process we can in that term as alpha compositing. Now we were using only two versions of alpha, alpha equals to 1 and alpha equals to 0. But in fact, we can use entire spectrum of alpha. It will be often also a channel of 8 encoded by 8 bits. And we can therefore have various mixtures of a foreground and background color, where the foreground will be partially transparent and partially opaque, and this could also vary across the image for each pixel. So this formula is basically, which you can recognize here, the linear interpolation is the alpha compositing. We can also perform alpha compositing in case when we would like to have some graphics elements rasterized on a background without any aliasing effects. So imagine that we will have a perfect triangle which we want to rasterize on a discrete resolution image, and this resolution, if at the vertices of the triangle, the triangle will be only partially covering an area of a pixel. Let's imagine that we are looking at this particular pixel here. So if we are scaling it up, then the triangle area will be only this much of the entire pixel. So the area corresponding to that pixel. So which color should this pixel have? The triangle color, or should it have the background color? And the answer is it should be a mix of both. Essentially, here we will be using similar concept to the alpha compositing as we were dealing with the transparency, where the alpha will be defined for the foreground color will be defined as a fraction of the entire area A. So this will be the area A, and the fraction of which is the area corresponding to the triangle. And the AT divided by A fraction will define as is equal to our alpha for the compositing. Now, you can also imagine that our triangle will be transparent. So we already have a transparency, the alpha value coming from the transparency itself. So this will be another alpha, and then we will need to essentially multiply the alpha, the transparency of the triangle, with the coverage ratio, the alpha which we have computed to avoid the aliasing. Finally, let me say a few words on the various image formats which we are having to our disposal. A very popular image format, which is used also in photography, is the JPEG format, which is the abbreviation for Joint Photographers Expert Group, which is a so-called lossy compressed image. So this means that not every pixel value is stored at each the position of the raster image, but only a fraction of the information is stored, and at the time of display, this information is uncompressed. However, not if we will have a uncompressed representation and then we will use the JPEG compression, we will not be able um, to reconstruct the uncompressed original representation perfectly. There will be some loss. So here we are therefore talking about lossy compression. However, the JPEG is a perception-inspired compression, which means that we cannot really discriminate very easily even very strong compression ratios with JPEG, and we would not be able to distinguish between the original and the JPEG compressed representation. This compression involves several stages, including an discrete cosine transform, and so on, to get rid of some high frequencies and give prominence to lower frequencies of the image, so that the values with which we can represent the image can be much less than the original representation. The very common format is the TIFF format, the so-called tagged image file format. And this is not just one file format, this is basically a family of image file formats, because you can have a grayscale TIFF representation, you can have an 8-bit TIFF representation, you can have a 16-bit per channel representation in a TIFF. And you can have it either uncompressed or compressed, but in a lossless way, meaning that the compression technique which is used in TIFF file format is lossless and will reconstruct the original image perfectly. This also means that the compression ratio will be probably not so high as for the JPEG images. Then we have another representation, which is the PPM. I don't know if you have heard about such a file format before, but such a file format is a simple uncompressed format. So it stores all the image values as they are in the original raster image. There is no compression going on. One can say, why would somebody like to have such an image file format if it will result into a big image? The memory requirements will be high. Well, it's because it is very simple to implement an PPM importer or exporter. So from the programmer's point of view, this is a very easy file format to handle. If we would need to write an importer for JPEG images from scratch, this will be a rather tedious task, and as opposed to an importer of a PPM file format. Finally, we are mentioning the PNG, the Portable Network Graphics representation, which was kind of an newer version of the previously known GIF file format. And the PNG is a lossless compressed image, and this lossless compression can also include an alpha channel. This means that the images will be already including the transparency, and if we will place in the web the image on certain background, the transparency can nicely blend in the image with the background color. And this is all for the raster images. Thank you for your attention today. And on the next time, we will be dealing with the core of the three-dimensional graphics with the ray tracing. See you soon.